My name is Rohan Dominguez, and this is my EEE120 Capstone project video. So for this project, we designed two synchronous sequential machines and then implemented and built one of them in digital. So basically, this is a circuit for controlling traffic lights at an intersection. So we have a main street and a side avenue. We have two inputs, C1 and C0, that determine the mode of operation. And there are six outputs, basically each of the lights for Main Street and Side Street, yet red, yellow, and green. So that's six. And our first mode of operation is 00, which is the normal, mode of operation that you would see at an intersection. So it might start at red, red, and then the next Main Street or Side Street would go to green. And then 01 is a flashing red and in both directions, and this is the equivalent of a four-way stop signal. 10 input is a flashing red for side avenue and flashing yellow for Main Street. And then 11 is basically any special state that you want to create, and this is basically the main differentiating factor between the two designs that we created. So for my first design, I wanted to have a flashing mode between all on and all off. So the assumption that we made for this design was that the machine uses a asynchronous reset to ensure that upon power up or reset, the system immediately enters state zero, which is red red for safety. And basically this prevents both streets from receiving a green light. And then our initial power on state, as I said, would default to state zero red red, kind of like a fail-safe mode. And our emergency mode, which is the main differentiating factor of this circuit, was for C equals 1, is that it represents a full system or major emergency, such as a natural disaster or blackout. And in this state, lights are turned on, and then all off to alert drivers that the signal is not operating normally. So here you can see my state definition table. So in both of my designs had seven states, but some of the states are different between them. So we start from state zero, which is red red, state one, which is red green, state two, which is red yellow, and the first color is the main street, and second color is the side street. State three is green green, state four yellow red, state five off, meaning all lights are off, and then state six is all on. As you can see the outputs that this would create on the side are, uh, are each of our six outputs, and then our binary assignment just represents the state number. As you can see, the first five states, meaning state zero to state four, represent the normal operations of a traffic light and things of that nature. And state five, off, off, is there for to have a flashing mode because obviously flashing needs to go from on to off. So anytime that there's a flashing mode, which is about most of our operations, actually just three out of four of them required to go to an off mode. So state five is used a lot. It's good to mention this is a more state machine. Here's my transition diagram. Just kind of just shows that when in one of the states, what output or for any specific output combination that is 00, 10, 11, and 10, where the where the circuit will go and which state it will go to. The state outcomes when I actually show you the design in digital. And here's my state transition table, which is just, taking values from the state diagram. My Carnot maps, obviously, I needed three 5 variable maps and then six 3 variable maps for each of the outputs, and then obviously each of the next state bits, which was the 5 variable maps. Here's my equations, and this is basically what I would use to implement this in digital and actually build the circuit. The circuit required 21 AND gates, 7 OR gates, and 3 asynchronous D flip-flops for the next 8 bits. So for my design two, so basically my C equals 1, which is my special state, was different on this one. So this would be a flashing yellow on Main Street, side avenue off, and basically it would flash between this the last state, and then on an on-off or all-off state, my bad. So the assumptions I made for this was that obviously the first two assumptions are the same as my design one. So we would use an asynchronous reset to ensure that the finite state machine starts at S0 red red upon restart or reset. And it's just like a safe mode. And on power up, the system begins in state zero, providing initial safe state. And this ensures no premature green signals are given before the system resets and stabilizes. And for C equals 11, we had a partial closure mode. So this is kind of like why I decided to choose this specific state and special state. So this corresponds to a temporary shutdown of side avenue, basically for construction or for low traffic late night scenarios or malfunction. Mainly, this is for like a shutdown of side avenue where traffic is only going through Main Street and indefinitely is closed on side streets. So that's why it's flashing yellow on Main and then everything else is off. So for the most part, the states are exactly the same as in my design one, so I won't really go into them again. But my seventh state or state six is yellow off. Um, Again, I already explained that, so that's just kind of how that's kind of my differentiating factor between my two designs. And how I made them functionally different is that if you implemented both in digital, you would see the lights be different and outcomes be different. And the functionality of C equals 1, 1, my special mode, is different between the two sequential machines. And I'll quickly scroll past my state transition diagram, state transition table, Carnot maps. The same amount of Carnot maps were required. Obviously, the equations were different since the transition tables were different. And we have 18 AND gates, 5 OR gates, and 3 asynchronous flip-flops. So less logic gates required, basically meaning it would be a simpler circuit. So now I'm going on to the criteria. So basically why I chose one design over the other. So first criteria, I had emergency handling effectiveness at 30%, logic simplicity, aka the gate count at 20%, simulation clarity or visual distinction at 20%, scalability and extendability at 15%, and my own personal confidence in designing and understanding this sequential machine at 15%. So these criteria were chosen and based on a combination of stakeholder interviews and engineering judgment. For example, my stakeholders emphasize an importance on clear emergency signaling. So design one's all on mode would prioritize that specifically because it would make it so drivers could easily see that there was an emergency. And then I assigned higher weights to those criterias. And then after scoring both designs, design one had a higher score, which is my all on, all off design, which is 82 versus 70, which then meaning design one was selected for implementation. I'll briefly go I'll briefly go over the individual scoring. So design one scored in every category except one scored higher, might I say. So design two scored higher in logic simplicity, 18 points versus 12 due to its lower gate count, but design one outperformed in key areas such as emergency handling effectiveness, 25 versus 15, since it's all lights on mode provides clear and high visibility during emergencies. Simulation clarity, design one got 18 and design two had 15. Just the, the the lighting pattern in design one enhances the clarity and engagement of the simulation, which is especially useful for presentation and debugging the circuit. Scalability, 13 points to design one, 10 points to design two. Design one's richer state structure and output control made it more flexible for future features like pedestrian control or maybe additional caution modes where it would go between multiple states. And then design understanding, 14 points to design one and 12 points for design two. This is just my own personal, I guess, bias towards picking the circuit. And that's why I kind of rated it less than the other categories. And I have a deeper understanding of design one's transitions and logic equations, which it was easier for me to debug and modify it and basically explain it in this video. To the actual fun part, and which is my actual circuit in digital. So you could see the 21 AND gates, the 7 OR gates, and the 3 asynchronous D flip-flops. So I used a lot of tunnels in this design just to make it more simple because I'd have just a lot of wires overlapping each other, and it's kind of easier to see and understand and basically, just explain how the logic works for this. And you can see our outputs, main red, yellow, green, side red, yellow, green, and they're colored LED lights. And we have our C1 input, C0 input, our clock, and our reset. Obviously, C1 is the leftmost bit, so every time the first bit I say is going to be C1, and the second bit I say is going to be C0. We also have our inverters to invert those inputs. So we're going to start out at a 0, 0 state, which is just our 0, 0 input, which is our normal logic operations. So obviously, again, like I said in my assumptions, it's going to start out with red, red. So both lights are red. We can hit the clock. We can go to state 1, which is main red, side green. And then we go to state 2, which goes back, side changes to yellow. State 3, which main changes to green, side changes to red. And then green obviously goes back to yellow. And then we go back to state 0, which is what do we call it? Red, red. So that's basically just 0, 0 is our normal logic operations. Nothing special is happening. Our street lights is just acting just as it should in like a normal real life setting. So now we can go on to our 1, 0 input. And this is where it flashes between red, red on both lights, and then off. So we can clock it, goes to off, clock it, goes to red, clock it, goes to off, off red. You can just click it over and over, and that's exactly what it's going to do. And then we can have our 1, 0 input, which is our flashing as main yellow and then side red. So we can hit the clock, main is yellow, side is red, and it just flashes on and off over and over and over again. Nothing else changes. And our final input combination, which is my personal creation and my special state for this circuit, is the 1, 1 input combination. So we can clock it. All the lights are on. It looks nice and pretty. And it goes all off. And no matter how many times I clock it, it still does the same thing. And then I can hit the reset just to show you how the reset works. It always goes back to 0. So show the state transitions when we're not in like the normal prescribed state. So say we're just using a 0, 0 operation, we clock it twice. Now we're in state 2. And then we change the input, sorry, to 1, 1. We should expect it not to just loop back into state 3. We should expect it to go to, at least in my state transition diagram, I wanted it to go to state 6, which is the all on state. So we can clock it and we can see how that exactly works. And then we can go back to our normal operations after this. And this wouldn't just loop back into state 6 again. This would actually just go reset back to state 0, which is our red, red state. We can do that a few more times just to show. So we're in this state right here. Let's say we want to go have a 1, 0 input. We want it to be main yellow and side red. So we'll just clock it. It'll do exactly that. And then now it'll just go between this mode of flashing between main yellow, side red, on, off. And we can do the same for our final input combination. So let's just clock it a few times, see where it is. And now it's at this main red, side yellow, but we want it to start flashing red in this current state. So we'll do 1, 0, clock it once, it'll go back to the red, and then it'll flash between on and off. And I could have made it go to state 5, which is the all off, but that would have just caused a lot of arrows to be going into state 5, and it just made my diagram a lot more complex. So this is just one of the design choices that I made. I was the EEE120 Capstone project video, and I'm Rohan Dominguez. Thank you for watching.